Hello everyone. My name is Krishna Priya V R. So I welcome you all to a demo lecture of linear algebra. So first of all, I would like to tell you what are the syllabus of linear algebra, which are a portion of the GATE XE. So in linear algebra, we will talk about what are matrices. We will understand what are the types of different matrices. We will study about the algebra of matrices, which includes matrix addition, matrix multiplication, etc. We will understand what are determinants. We will understand what is meant by inverse of a matrix, whether a matrix is invertible or not. We will study what are eigenvalues and what are eigenvectors. We will understand what is meant by diagonalization of a matrix. We will understand whether a matrix is diagonalizable or not. And finally, we will study what is meant by Cayley-Hamilton theorem. So in this today's demo lecture, I'm going to talk about what are matrices, and we will go through some of the different types of matrices, and we will study what is matrix multiplication. So to start with, what is a matrix? So matrix is a rectangular array of numbers or functions arranged in m rows and n columns. So if there are m rows and n columns, we will say that the size of the matrix is m by n, where m is the number of rows and n is the number of columns. So usually we denote matrices by capital letters, and suppose if we have a an element, arbitrary element of a matrix Aij, it is represented by Aij, where it is an element in ith row and jth column. Okay, so a element in ith row and jth column will be denoted as Aij. In general, suppose if I am writing a matrix capital A, then it will be written as A11, which is the element. These are the rows. Okay, these are the rows and these are the columns. So we will write the first element, element in first row and first column as A11. Similarly, first row, second column as A12, etc. The element in first row and nth column as A1n. Similarly, second row as A21, A22, etc. A2n. Similarly, last, the element at the mth row is written as AM1, AM2, etc. AMN. Okay, so if I am writing another example of a matrix, suppose if I am writing 2, 3, 1, 0, minus 1, 0, how many rows are there? There are 3 rows, 1, 2, and 3. So there are 3 rows. How many columns are there? 1 and 2. So this is a matrix of size 3 by 2. So there are different types of matrices. So first I am going to talk about what is meant by a square matrix. A square matrix is a matrix where number of rows is equal to number of column. That is, m is equal to n. For example, if I am writing an example, here 2, 0, minus 1, 1. What is the size of this matrix? 2 by 2, right? There are 2 columns and 2 rows. So what is m here? M equal to n equal to 2. Such matrices are called square matrices. So square matrices contain something called a principal diagonal element. So principal diagonal element means the elements that belong to the diagonal. So this is called principal diagonal. So for this matrix, suppose I call this A, the principal diagonal elements are 2. Principal diagonal elements are 2 and 1. If I am writing another example, suppose 2, 0, 1, 1, minus 1, 0, 0, 0, 0. If I am writing what are the principal diagonal elements? The elements which are present in the diagonal, which are 2, minus 1 and 0. So when we have a square matrix, it will have a principal diagonal elements. Then another term which we have to know is what is meant by trace of a matrix. Trace of a matrix means sum of the principal diagonal elements. So suppose this is a matrix A. Can you tell me the size, the trace of A?
-3.
It is sum. Can you just check it again? The sum of the elements of the diagonal are the is called the trace. What are the diagonal elements? 2, -1 and 0. What is the sum? 2 plus -1 plus 0. What is it?
1.
1. So the trace of this matrix is 1. So there are so many properties relating to trace of the matrix. Some of the properties are, simple properties are, if I am multiplying a matrix with some scalar, okay, then the trace of that matrix, if I am multiplying a matrix with some scalar, then the trace of that matrix will be equal to that scalar times trace of A. Suppose I am taking this matrix, okay, this matrix 2, 0, -1, 1. I am multiplying it with 2. Our scalar is 2. What is the corresponding matrix? We will multiply each element of the matrix with this scalar. So the resulting matrix will be 4, 0, -2, 2. So what is the trace of this matrix? Trace equal to 4 plus 2, 6, which is equal to 2 times trace of this matrix. Trace of this matrix is 3. So this will be 2 into 3 equal to 6. So this is one property. Another property is trace of A plus B is equal to trace of A plus trace of B. You can actually check it with different matrices. I'm just writing the property here. Another property is trace of AB is equal to trace of BA. That is, if I'm multiplying two matrices A and B, and if I'm taking the trace, it will be same as if I'm multiplying B and A. So another type of matrix is called diagonal matrix. The definition of a diagonal matrix is that it is a square matrix with elements, with all elements except principal diagonal elements are 0. That is, everything except the principal diagonal elements are 0. For example, 2, 0, 0, 0, -1, 0, 0, 0, 1. In this matrix, all the elements except the principal diagonal elements are 0. Such type of matrices are called diagonal matrices. Now, another type of a matrix is called scalar matrix. So, scalar matrix is a type of diagonal matrix whose principal diagonal elements are equal. Elements are equal. Here we have seen an example where principal diagonal elements are different, but they are non-zero. In a scalar matrix, a principal diagonal elements are equal. For example, here all the principal diagonal elements are equal to 5. So another type of matrix is a unit matrix. Here, all the diagonal entries or the principal diagonal entries are 1. It is also called identity matrix. A 2 by 2 unit matrix is 1, 0, 0, 1. This is a 2 by 2 unit matrix or identity matrix. And it's a 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. All the diagonal elements are 1. So such matrices are called unit matrix. The null matrix is a type of matrix where all elements in that matrix are 0. From the name itself, we can know that all elements, it's null, nothing is there. So all elements are 0. I am writing an example 0, 0, 0, 0. This is a 2 by 2 null matrix. Okay, now we are going to another operation of a matrix called transpose of a matrix. Here, what do you mean by transpose? Transpose means interchanging rows into columns or columns into rows. I will tell you with an example. Before that, transpose is usually denoted as A with a superscript T or A dash. Okay, so if I am writing an example, if I am writing a matrix, some A is equal to A, B, C, D, E, F, G, H, I. This is a matrix. So what is A transpose? In A transpose, we will write the row as column. We will write this second row as second column. Write third row as third column. This is called transpose of a matrix. Okay, for another example, suppose B is equal to 2, 3, minus 1, 0. What is B transpose? 2, 3, and next row is minus 1, 0. I hope you understood. Right, everybody understood till this much?
Yes, ma'am.
Yes, ma'am.
Okay, now that is in other words, the element in ith row and jth column becomes an element in jth row and ith column. Okay, so now we are going to talk about some of the properties of this transpose. One property is that A transpose, the whole transpose will be equal to A. We can take this example. Suppose B. We have B here, B transpose here. If I am taking B transpose, the whole transpose, what will it will be? We will write the rows as columns, which is equal to B, right? So A B transpose, the whole transpose is equal to B. In general, A transpose, the whole transpose will be equal to A. Another property is A plus B, the whole transpose will be A transpose plus B transpose. Another property is K into A, the whole transpose will be K into A transpose. Suppose if I am multiplying this B matrix with a scalar 2. So 2 into B is equal to 4, 6. We will multiply each element with 2. Minus 2, 0. If I am taking 2B, the whole transpose, what will it be? 4, 6, minus 2, 0. Which will be, if I am taking 2 outside from this matrix, it will be 2 into 2 minus 1, 3 and 0, right? Which is equal to 2 into B transpose, right? So K into A, the whole transpose, in general, K into A, the whole transpose will be K into A transpose. Similarly, we can just try it at home, this one. Take two matrices, random matrices A and B, take their transpose, check whether it is equal to the sum of the transpose of those matrices. So another type of matrix that I want to tell you about is the symmetric matrix. Symmetric matrix is a square matrix with Aij will be equal to Aj for all I and J. I will give an example, it will be more clear. For example, we have some matrix A is equal to 1, 2, 3, 2. Okay. So here, what is A11? A11 is the element in the first row and first column. It is equal to 1, which is equal to A11, right? I and J are the same. So I am taking A12. What is A12? Is the element in first row and second column, which is 2. 2 is equal to, what is A21? A21 is also 2, which are same. Similarly, A13 is equal to 3, equal to A31. We can see that Aij is equal to Aji for all I and j. Such matrices are called symmetric matrices. There is another way to check whether a matrix is symmetric or not. That is, we calculate what is A transpose. We take transpose of this matrix. The rows will become columns 1, 2, 3. Rows will become columns 2, 4, 5. Rows will become column 3, 5, 6. We can see that A is equal to A transpose. So if you want to check whether a matrix is symmetric or not, take the transpose. If the transpose of that matrix is equal to that matrix, then we can say that it is a symmetric matrix. It's an important property, keep it in mind. Another type of matrix is square matrix, skew symmetric matrix, which is a square matrix with Aij is equal to minus Aji for all I and j. For example, if I am writing a matrix A is equal to 0, 1, minus 2, minus 1, 0, 3, 2, minus 3, 0. Okay, here what is A11? A11 equal to 0, right? Which is equal to minus of A11 because negative of 0 is 0 itself. What is A12? A12 is 1, right? First row, second column. So A12 is 1. What is A21? A21 is second row, first column, which is minus 1. From this, we can see that A12 is equal to minus of A21 or Aij equal to minus of Aji for I equal to 1, j equal to 2. Similarly, A13 is equal to minus 2, A31 equal to 2. We can see that A13 is equal to minus of A31. Similarly, you can see for all other elements, they will be the negative of each other. And another way to find out whether a matrix is skew symmetric is that similarly for symmetry, we will find out what is A transpose. When we do the transpose of A, it will become column 0, 1, minus 2, minus 1, 0, 3, 2, minus 3, 0. If I am taking a negative out of this, or if I am multiplying a minus 1 to the matrix A here, we will get this matrix. So A transpose will be negative of A for a skew symmetric matrix. So this is also important. For a symmetric matrix, A transpose will be equal to A, and for a skew symmetric matrix, A transpose will be equal to negative of A. So also note that, for a skew symmetric matrix, we can see that all the diagonal elements are 0, because otherwise if A11 is 1, it will not be equal to negative of A11, right? So note that all principal diagonal elements of a skew symmetric matrix are 0. Okay. Now we will go to a property of this symmetric and skew symmetric matrix. This property states that every square matrix can be expressed as a sum of symmetric and skew symmetric matrix. That is, if I have a square matrix, it can be written as a sum of a symmetric and skew symmetric matrix. I will tell you how. If I have a matrix A, okay, it can be written as half plus half into A, right? Half plus half equal to 1 into A is equal to A, which is equal to half into A plus half into A. I'm just taking this A inside, that's it, which is equal to, now I'm subtracting and adding a half of A transpose. Okay, half of A plus half of A transpose plus half of A minus half of A transpose. This half of A transpose and minus of half transpose will get cancelled and it will be the same. So now I'm just grouping it together. I'm taking half outside and A plus A transpose. Now plus, I am taking half outside, A minus A transpose. We will see that if I am taking an example, I will show you this matrix will be a symmetric matrix and this matrix will be a skew symmetric matrix. So, given a square matrix A, it can be written as the sum of a symmetric matrix and a skew symmetric matrix. Example, if I have a matrix A is equal to 1, 2, 3, and 4. Okay, now what is A transpose? A transpose is 1, 2, 3, 4. Right, rows as columns, rows as columns. Now, if I am calculating half of A plus A transpose, which is half of what is A? 1, 2, 3, 4 plus A transpose 1, 3, 2, 4. When we add two matrices, we do the element wise addition. That is 1 plus 1, 2, 2 plus 3, 5, 3 plus 2, 5, 4 plus 4, 8, which is equal to 1, 5 by 2, 5 by 2, 4. We can see that this is a symmetric matrix, right? Because A11 equal to A11, A12 is equal to A21, A22 equal to A22. So this is a symmetric matrix. Now, if I am calculating A of A minus A transpose, is equal to half of 1, 2, 3, 4 minus 1, 3, 2, 4. We similarly, like in addition, we also do the element wise subtraction, which is 1 minus 1, 0, 2 minus 3 minus 1, 3 minus 2, 1, 4 minus 4, 0. This is equal to 0 minus 1 by 2, 1 by 2, 0. We can see that this is a skew symmetric matrix. All the diagonal elements are 0 and also A12 is equal to minus of A21. So when we add these two, half of A plus A transpose plus half of A minus A transpose, that is, we are adding up a symmetric and skew symmetric matrix, we will get 1, 5 by 2, 5 by 2, 4 plus 0 minus 1 by 2, 1 by 2, 0, which is equal to 1 plus 0, 1. 5 by 2 minus 1 by 2, 2. 5 by 2 plus 1 by 2, 3. 4 plus 0, 4, which is equal to the matrix we started with A. So a matrix A can be written as the sum of a symmetric matrix and a skew symmetric matrix. So this is an important property you need to remember while solving questions. So next I am going to talk about some other type of matrix called triangular matrix. Triangular matrix, there are two types of triangular matrices. One is upper triangular matrix and two lower triangular matrix. So from the name itself, we can easily understand what is meant by upper triangular matrix. So upper triangular matrix is a square matrix whose elements below the principal diagonal are 0. If I am giving an example, suppose we have A equal to A, B, C, 0, D, E, 0, 0, F. We can see that all elements, this forms a triangle, right? This forms a triangle in the upper part of the matrix. So all the elements below the principal diagonal are 0. Since this is called upper triangular matrices. Some triangle is formed in the upper part of the matrix. Similarly, we have lower triangular matrices. From this definition itself, we can understand what is meant by lower triangular matrix, right? A square matrix whose elements above the principal diagonal are 0. For example, A 0 0 B, C, 0, D, F. From this, we can see that all the elements above the diagonal are 0 and there forms a triangle-like shape in the lower part of the matrix. So such matrices are called lower triangular matrices. Okay, these are some of the type of matrices we see very often. Now I will tell you about some algebra of matrices, such as multiplication of two matrices, and then we will go on to the different types of matrices. Like we need multiplication of matrices to understand what are the next type of matrices. So regarding multiplication of matrices, for multiplication of will a multiplication of two matrices make sense? Suppose if I have a random two matrices A and B, can I always multiply such matrices? So if I have a matrix A and B, we cannot always multiply these matrices. Multiplication of two matrices are possible only when number of columns of first matrix is equal to number of rows of second matrix. That is, in general, if I have a matrix A of size m by n and matrix of B n by p, then only we can multiply these two matrices. If this is some n, j or I or different value, we cannot multiply these two matrices. We can only multiply these matrices then number of columns of A is equal to number of rows of B. Then the product matrix C, suppose A into B equal to C. This matrix will be of size m by p, m by p. So if we have a matrix of size m by n and n by p, it will result, multiplication of those matrices will result in a matrix C of size m by p. So how does we multiply two matrices? Suppose I have a matrix A equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, and some B is equal to B11, B12, B21, B22, B31, B32. What is the size of this matrix? Number of rows 3, number of columns 3. So this is a 3 by 3 matrix, and here B is a number of rows 3, number of columns 2. So this is a 3 by 2 matrix. Will the multiplication is the multiplication possible? Yes, because number of rows, number of columns of the first matrix is equal to the number of rows of the second matrix. So this multiplication is possible. So suppose this gives us A into B gives us a matrix C. What will be the size of C? It will be 3 by 2, right? So if I have a 3 by 2 matrix C, C11, C12, C21, C22, C31, C32. It will be a 3 by 2 matrix, right? A and B gives C, which is a 3 by 2 matrix. Now, how to calculate the C11, C12, C22, C1, etc. So how we calculate this using, I will explain now how to calculate C11, etc. Suppose I name the rows of this matrix as A1, A2, and A3. Okay, A1 is the first row, A2 is the second row, A3 is the third row. And the columns of B as B1 and B2. Okay, then we will see that C11, that is the first element or the first element in the first row and first column of this product is equal to A1 into B1. We multiply the row of the first matrix, first row of the first matrix with the first column of the first matrix to give the first element in the first row and first column. Also, in other words, what I meant by multiplication is we multiply the element wise. That is, A11 is multiplied with B11, A12 is multiplied with B21, A13 is multiplied with B31. So it will give A11 B11 plus A12 B21 plus A13 B31. So that is the element of C11. Similarly, if I want to write the element C12, C12 is obtained by multiplying the first row of matrix A with the second column of B. C12, first column of A with second column of B, which is equal to, when we multiply that, we will get A11 B12 plus A12 into B22 plus A13 into B32. Similarly, we can calculate what are C2. What will be the C21? C21 we will multiply the second row of A to the first column of B. C21 21. Similarly, C22 we will multiply A2 into B2. Like that it goes. I will explain you with an example also. Suppose we have a matrix A equal to 2, 3, 1, 0, which is a 2 by 2 matrix. And a matrix B is equal to 3, 1, 0, 0, minus 1, 2, which is a 2 by 3 matrix. Is this multiplication possible? Yes, because 2 equal to 2. The resulting size of the matrix will be 2 by 3. Okay, so how will A and B, A into B looks like? We will multiply this row with this column, this row with this column. So this will give 2 into 3 plus 3 into 0, which is equal to 6. And next, what will be the next element? We will multiply this row with this column. It should be 2 into 1 plus 3 into minus 1, which will be minus 1. Similarly, we will multiply this row with this column, which will give the third element, which will be 2 into 0 plus 3 into 6. Similarly, when we calculate it, it will give this matrix, which is a 2 by 3 matrix, 2 rows and 3 columns. Okay, so one of the property of this multiplication of matrices is that you cannot always multiply two matrices. If A into B makes sense, it does not guarantee that B into A should make sense. Suppose in this example itself, it is a 2 by 2 matrix and a 2 by 3 matrix. A into B, we got the product. But can we do BA? We cannot, because B is of size 2 by 3 and A is of size 2 by 2. These two are not equal. So B into A does not even exist. So A into B, if A into B exists, does not guarantee that B into A exists. So this gives us one of the property of matrix multiplication, that AB will not always be equal to BA. Okay, for example, if I have a matrix A is equal to minus 1, 0, 2, 3 and B is equal to 1, 2, 3, 0, the A into B, we will get it like minus 1 into 1 plus 0 into 3, minus 1. Minus 1 into 2 plus 0 into 0, which is equal to 2, minus 2. Then 2 into 1 plus 3 into 3, which is equal to 11. And 2 into 2 plus 3 into 0, which is equal to 4. What is BA? BA will be multiplying this one with this one. That is 1 into 2, 1 this row with this column. 1 into minus 1 plus 2 into 2. We will get 3. Similarly, we will get the rest as this one. Here we can see that AB not equal to BA. I hope everyone understood till then. Is there any doubt or?
No, ma'am.
Okay. Okay. So I want to try you a homework. Given a matrix, A is equal to 1, minus 2, 3, minus 4, 2, 5, and B is equal to 2, 3, 4, 5, 2, 1. I want you to check whether if AB is equal to BA or AB not equal to BA. Okay. Now another property of a matrix is AB, the whole transpose will be equal to B transpose into A transpose. This also we can try. If I have a matrix A is equal to 1 minus 4, 3 and B is equal to minus 1, 2, 1. What will be AB? AB equal to 1 into minus 1, minus 1. 1 into 2, 2. 1 into 1, 1. Minus 4 into minus 1, 4. Minus 4 into 2, minus 8. Minus 4 into 1, minus 4. 3 into minus 1, minus 3. 3 into 2, 6. 3 into 1, 3. This is AB. Okay, if I am taking transpose of AB, AB the whole transpose will be equal to minus 1, 2, 1, 4, minus 8, minus 4, minus 3, 6 and 3. You can check by yourself that AB the whole transpose is equal to B transpose into A transpose. Take the transpose of B. B transpose will be minus 1, 2, 1, right? A transpose will be 1, minus 4, 3, right? Transpose of a 3 by 1 matrix will be a 1 by 3 matrix. Transpose of a 1 by 3 matrix will be a 3 by 1 matrix. Okay. Now, if we calculate B transpose into A transpose, we will get exactly the same answer as minus 1, 4, minus 3, 2, minus 8, 6, 1, 1, minus 4, 3, which is equal to AB, the whole transpose. These are two, there are so many properties. These are one of the two important properties regarding matrix multiplication. Okay, now let's wind up the class with a question. So I'm giving you a question. Just try it out by yourself. Given a matrix X, Y, and P of sizes given as 4 by 3, 4 by 3, and 2 by 3, find out what is the order or what is the size of the matrix P into X transpose into Y into P transpose, the whole transpose. Okay, let's try it out. What is the size of P? Is 2 by 3. What is size of X? 4 by 3. Implies X transpose will be of size 3 by 4. If I have a matrix of size M by N, then A transpose will be of size N by M because we are interchanging rows and columns. So X transpose will be 3 by 4. Y will be 4 by 3. So what will be the product? X transpose into Y will be of size. Is it possible? Yes, because X transpose has number of columns 4, Y has number of rows 4. So the size of the matrix will be 3 by 3, right? 3 by 4 into 4 by 3. There's resulting will be 3 by 3. And what is the size of P transpose? P is of size 2 by 3. P transpose is of size 3 by 2. So now we can calculate P into X transpose into Y. What will be the size? Size of P is 2 by 3. Size of X transpose Y is 3 by 3. What will be the size of this matrix? It will be 2 by 3, right? Because it's 3 and 3, the matrix multiplication is possible. And if I have a matrix of size M by N and N by P, I have a other result. The multiplication of the matrix will give a matrix of size M by P. So like that, 2 by 3. So I multiply P into X transpose Y into P transpose. This one is a matrix of size 2 by 3. We calculated here. P transpose is a matrix of size 3 by 2. What is the resulting matrix is of size 2 by 2. Now, what is the transpose of a 2 by 2 matrix? It will be 2 by 2 itself. If it is an M by N matrix, the transpose will be N by M. If M and N are equal, then 2 by 2, the size of transpose of a 2 by 2 matrix will be 2 by 2 matrix. So the answer will be 2 by 2, 2 by 2. So option C is correct. Just try it out yourself. Just work it out yourself. That will be better. So I'm ending today's section. So we will learn about more types of matrices, what is meant by inverse of a matrix, what is meant by determinant, what is meant by eigenvalue, eigenvectors, etc. in the coming sections. So please join the class if you want to learn more about matrices. So thank you so much.